So this brings us to lecture 37 on Gauss's theorem, also known as the Divergence Theorem. And I mean, here's the theorem right at the top, right? The integral of the divergence over a volume is equal to the integral, well, the surface integral of the same vector field over the boundary of that volume. And to start with, we think about the volume, or the B, as being a simple solid, meaning that it's a solid with no holes in it. And then by the time we're done, we'll have, allowed B to have holes, and there's like a natural generalization of the version of the divergence theorem with no holes to the divergence theorem with holes, just like we've seen for the Green theorem and Stokes theorem before, right? So the first proof I'll share is essentially an intuitive argument. It's in some sense an infinitesimal argument, and it's based on basically extending the divergence theorem version of Green's theorem, which was based on the discussion of two-dimensional flux to three dimensions. And the way to do that is to think about like a little sort of a little disk, if you will. And there are, well, there's the side of the disk, which I've made sort of this, I don't even know what this color is, a Dr. Seuss flesh color, and then this blue up here. So there's the top, there's the bottom, and there's the sides, right? And so, like I said, to consider an infinitesimal cylinder E, which is the disk Cartesian product with delta Z. Now, if the dz bothers you, you could, of course, say that this is the disk Cartesian product with like the closed interval to Z for a fixed Z to like Z plus delta Z for a finite but small delta Z, right? I mean, that's all I mean by that, is it's a little tiny little cylinder. And so I can think about the flux of the vector field through this cylinder with caps in terms of three things: the up, the down, and the side. And the side, if I want to count the number of field lines going out the side, I can basically, I'm going to be able to use Green's theorem, the flux form of Green's theorem, which said that the flux through a curve, the boundary of D, right, would be this. And so if it's essentially very small, then I can just multiply this by the delta Z to get the flux through the curved edge. That's the one idea. So I'm connecting the idea of two-dimensional, like flux of a curve in 2 dimensions and 3 dimensions in perhaps the natural way there, although admittedly there's like a jump, right? There's a little bit of a jump there, that idea. And then of course to calculate the flux through the upper and lower, well then I'll just straight up do the, I'll calculate the integral. And so first of all, the flux through the horizontal strip, the curved piece, is going to be given by this integral times delta Z, but I'm also using the identity that delta Z is the integral over this interval. Let me call this interval I. Integral over this interval I of dz, right? I mean, let's go, because it's just Z evaluated from, well, Z to, I probably should put like a Z sub naught here or something, I don't know, but it's going to get obnoxious very soon. I tell you what the really obnoxious thing is, I'm just writing off the paper, dummy. So delta Z would be like integral of dz over that interval, which is of course just Z evaluated, and the Z naughts cancel, and you're just left with the thickness of the cylinder, right? So like the base point Z naught is essentially irrelevant, except that that's where the vector fields are going to be evaluated in this actual calculation. But anyway, taking, bootstrapping up from Green's theorem, the flux version of Green's theorem, and then times, well, I just said times dz, but, perhaps, I do think that I probably should go back in through here. Instead of putting dz here, put like delta z, and make it less sort of mystical, if you will, because some people have well, anyway. So then I could trade this double for this corresponding triple integral, right, where, like that. Okay, so that's part of it. That just accounts for so basically the flux through the curved side is gotten by the triple integral of this part of the divergence. But for the vector field PQR, there's also there's also this RZ hat part, Now RZ hat part we could ignore on the sides because the normal to the sides has no Z component. So like when you take the dot product of F with ds for the sides, the R was irrelevant. That's part of this argument, all right? But of course for the caps, the R part is not irrelevant. In fact, it's the whole story. So let's see here. So I got the flux. Where am I? Uno momento. All right, so the cap's at D cross, and I guess I put a sub naught on it. I'm not going to do that. I mean, anyway, so the lower part and the upper part, upper cap. In the upper one, ds is z hat dx dy. In the lower one, ds vector is minus z hat dx dy, right? Because, well, it's the upper and the lower. And so when you calculate the flux of the upper, you get R like that, and down you get R like that. And so we have, when we add those together, we just get the difference of R at xy fixed, z plus delta z minus R of xy z. And of course that's exactly the integral of this derivative, right? So using the fundamental theorem of calculus to convert this difference to that integral over the triple integral. And then so you got this plus that up there, and then put it all together. Bam, divergence theorem. But of course, this is only the divergence theorem, derived over a little pillbox, if you will, over a little cylinder. I don't know why I call it a pillbox, not really a pillbox. Anyway, so there, and then of course, what can you do? So if we can prove the divergence theorem over a little shape like that, then maybe we can sort of chop the space up into little pieces like that and add the divergence theorem on each little piece together to get the result for a more interesting shape. And that's one way you could argue, in fact. I have a proof of the divergence theorem for like a reasonably, at the end of this section I have a proof that actually characterizes the solid in terms of one of our typical breakdowns of a volume as it relates to the triple integration. And there's a more careful proof of the divergence theorem for a reasonably simple solid towards the end of this section. We'll get to it eventually. But anyway, that's the celebrated theorem of Gauss, the divergence theorem. And let's see here. So if you and then so I'm saying we've proved it for a simple shape, but you could just as well we proved it for an infinitesimal in some sense. I think prove is the wrong word. We have argued it's reasonable for a very thin solid, but in fact you can do it for any simple solid, a solid without holes like this. And all right, so let's see if I've got a picture. No, maybe I don't have that picture. Sometimes I try to draw a picture, like you can imagine there's sort of like a three-dimensional blob picture. You could imagine taking that three-dimensional shape and like cutting it into little slices like this, and then I can't do the picture justice. I mean, it's just like a bunch of thin little slices, and you could let those thin little slices sort of fill up the simple shape. And then if you think about each one of those like little regions that we have almost proved the divergence theorem for, then when you look at the integral of the triple integral of like adding these all together, then the triple integral of each little one's just going to add together to give the union of the shapes, which is the total. We're just using the additivity of the integral to get the divergence over the whole volume, and that's fine. The flux is more interesting, of course. Again, what happens is that like each one of these little subregions, it's oriented outward, and so when you put them together, what happens is just like we've seen before, like the left one would have, let's look at the connecting face. So from the left one, you've got a normal that is like that at the interface, right? For the right one, you've got an outward pointing normal, which is like, you know, this at the interface. But it's the same point set, right? It's the same point set that's shared by both of these subregions, subvolumes, if you will. And so on that subvolume, that cross face, if you will, the meeting face, the flux cancels. And so as you add those all together, you end up with just the exterior of the whole solid. So it's that same breakdown that we talked about for Green's theorem and also for Stokes' theorem. In fact, there's got to be a way to do this kind of argument, like in the abstract and more general, because you know, you start to see this like same pattern of idea that maybe we should generalize an abstract. And in fact, that's actually what's needed to prove what's called the generalized Stokes theorem. But that's not yet. We're going to get there. I'm not going to prove the generalized Stokes theorem. I'm just going to state it for you. But anyway. All right. So perhaps I have an example. Here's a nice example. Suppose your vector field. Let me actually show you the example, not just talk about it. Suppose the vector field is x plus y. I can zoom in a little bit more here. All right. So you got this vector field, x plus y, y plus x, z plus y. We wish to calculate the flux of f through a set of stairs which has width 3 and 10 steps, each of which are height and depth 1. Ugh. This is a horrible idea. I mean, what a horrible thing to ask to calculate, you know? So if I see if I can draw 10 steps, right? So 1, 2, 3, 4, 5, I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, not the, trying to make it to scale. I failed, obviously, right? So there's a set of steps, and then they're width 3, right? Am I really committing to drawing this whole thing? What have I done? Why did I make 10 steps? This example would have been perfectly fine with 3 steps. Goodness gracious, what is wrong with me? Those are supposed to be straight steps, but as you can see, my picture is degrading as further I get further up. Anyway, the width of these is 3, right? Well, width 3 and 10 steps, each height 1, so this makes this 10, right? And that makes this also 10 because they each have a depth of 10, 1 unit as well. And I said let E be the set of stairs and the boundary of E the outward oriented surface. So the boundary of E, good night. It's got the sidewall, the back sidewall, the tall straight sidewall that I'll kind of illustrate here, right? It's got the base that meets the floor, right? And then it's got like the front faces and the top faces of all the stairs. I don't know. I'm guesstimating. There's like a little around 30, not quite. I could count it exactly, but there's a lot of different subsets here. If you were to calculate the flux directly on this thing, it would be truly horrible. But this we can actually calculate with the divergence theorem pretty easily. Because the divergence of this vector field is 3, and so to calculate the flux through the boundary of E, we just have to calculate the integral of 3 dV, which is to say 3 times the triple integral of dV. In other words, the flux is just 3 times the volume of the stairs. And you could calculate the volume of the stairs easy enough, right? It's like 30 plus 27 plus, maybe 30 plus 29. No, 30 plus 27 plus 24. Do I have it? Oh, I was smarter here. 3 plus 1 plus 2 plus 3 plus 4 plus 5 plus blah, 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 blah. So, in fact, 165 would be the flux to whatever system of units we're using. Oh, that's the volume, rather. 3 times that is 495. So, yeah, that's the divergence theorem. So do you need to know this going into the next test? I mean, yes. Because if I ask you to calculate this flux, goodness gracious, you definitely don't want to calculate the flux of the vector field through this set of stairs, the the boundary of the set of stairs, just using direct calculation. It would be truly horrible. All right. And challenge, work the previous example for n stairs. What's wrong with me? Why am I even asking such a thing? Goodness gracious. What an idiot. Anyway, now here's that thing I said I'd come back to. Actually, I don't need to come back to because it's right here. So let f be a differentiable function at all, differential vector field rather, at all points near a simple solid E. Calculate the flux of the curl through the boundary of E. So the flux, so the divergent, the flux of the curl by Gauss's theorem is the divergence of the curl integrated over the volume. But one of our fundamental identities was that the divergence of the curl is 0. So we get 0. Yay! We gave a rather different argument before where I chopped the volume input into two pieces, and we used by Stokes' theorem that like the cutting, the equatorial circle where they met was differently oriented for the lower and upper half of the boundary of the bounding sphere. And you can generalize that to a closed surface, but this is obviously easier. Problem. Consider the cube E with side length L and 1 quarter at the origin. So that is, let's see if I got a picture here I can draw maybe. So basically we've got do, and then 1 corner is at the origin, right? So here's Z. All right. And I want to calculate the flux of the vector field xyz through the upper face of the cube. Ew. It's kind of nasty. What's the flux through this, just this face, right? Now, of course, you could just directly calculate it. It wouldn't be the end of the world. That has parameterization xy, and z is 1. And so you could calculate it. It wouldn't be that bad. But here's an argument with the divergence theorem. So what you do is you think about a bigger shape, imagine expanding this into a large cube, which so it has the origin at the center, right? Then if you did that, you can see that that larger cube, which is going this larger cube is -1 to 1 Cartesian product of itself 3 full times. And so and there's 6 faces, and each one of those 6 faces has 1 of these squares. And by the symmetry, there's no difference between this square and the others on that larger cube. It wouldn't be true on just the cube which we started with. The cube which we started with, there's a difference between the faces which are at the origin versus those which are out here. I mean, it is true that if I was to study this face and that face, these 3 would have the same flux by symmetry, but the inner 3 would not. And it's not at all clear how exactly that would play out. But anyway, if I look at the larger sphere, then the red patch is symmetrically situated with respect to the origin of all the other sub-quarter faces. And so it stands to reason that 1/24th of the total flux through the large cube is going to give me the flux of the red piece. All right? And so... Oh, and I've replaced L with 1. Sorry about that. But, I mean, I should do minus L to L. And so you just apply the divergence theorem on the large cube. Since the divergence of the vector field xyz is just 3, we have 3 times the volume of the large cube, which is 24L cubed, right? And then, so, seems wrong. I'm missing some dimensional constant in the vector field. Sorry about that. But anyway, so that would make the by the symmetry, 1/24 of that, in other words, is just L cubed, given the current system of units. The flux is just 1/24 of the total flux through the whole cube. That is a pretty popular physics question. Like, we ask this, the physics instructors ask this question in the context of Gauss's law, like, all the time. It should include picture here. All right, well, oh well. I mean, I will. Have I gotten pages out of order? Oh, no, this is just, so now the divergence theorem with holes here. And so I never can draw the holes inside the shape, go figure, but what I can attempt is a picture of the, like, here's the solid, right? And here's the other half of the solid. I'll kind of cut it in the middle and show you what's in the middle. So there could be like a hole in the middle, right? And that hole, it's into the surface, right? So like the rule is, if this is if this is E, altogether it's E, then like the outward pointing normal is like this, right? And likewise over here, you know. And then if there's a hole in the middle, it again points out of the volume, all right? But that means that it has to point like this. So the orientation of the surface of the inner holes is inward pointing. This is just the next analogous case to like our story about clockwise oriented holes for a counterclockwise oriented outer edge. So we have inward oriented holes in a simple, well, this is no longer a simple solid. For a solid with holes, the holes must have an inward orientation, whereas the outer edge of the solid has to have an outward orientation. That's the so-called positively oriented edge. That's what we mean. And with respect to that choice of orientation, there is a divergence theorem, and it's just what you'd expect. It's the integral over the boundary is equal to the triple integral of the divergence over the over the whole volume, just like that. And basically, you just take it and divide it, chop it up into pieces, and apply the divergence theorem to each piece separately. And then, when you put it back together, the you find that what was outer for half becomes inner for the whole. You know, like if I just look at the half, then this ds is not inward pointing, right? It's out of that half, and it's out of this half, right? But when you put it together, it's pointing into the whole. So anyway, there's that. And of course, there's also a deformation theorem correspondingly that says that if you have, if you have a vector field which has divergence 0 everywhere, except for perhaps at some holes, then if you encircle the holes with little, you can encircle the holes with like a little, the edge of the hole, if you will, and do the flux over the holes. Well, that's going to be equal to the flux over the outer edge. So this is very useful for the study of electrostatics. And of course, that's what I'm next going to study in here. But I don't think I require you to, I don't think I've asked you any questions about this. If you're interested in physics, it'd be good to read it and understand it. There's something interesting that goes on in here. Let's see if there's any more math I need to share with you. I don't think so. So I'm going to skip past that. And then the proof of the divergence theorem for rectangular solid is at the end of this section, right? And so I looked at a solid with 6 faces, and I think what I'm doing here is I'm proving it for a rectangular solid. If we can prove it for a finite rectangular solid, then we can chop another more interesting solid up into a bunch of like cubes, basically a bunch of rectangular solids, and then use that summation argument I was sketching before. And so like the proof that the divergence theorem goes over a solid with these 6 faces is lengthy, and then again it's like set up the surface integral and then break it down for the parameterization, identify which piece that gives you, where it's evaluated, and then look at the fact that, oh, look at that, that actually gives me a difference where the y and the z are fixed but the x is varying, and we're going from x2 to x1, so I might as well say it's the integral of the derivative of p with respect to x holding y and z fixed from x1 to x2 to get back. So it's again like the net change theorem, if you like. And that happens again and again to get all of that together. You need 3 times for each pair of faces. Each pair of faces picks up a derivative of the corresponding dimension. And put it all together, that gives you the divergence theorem for a rectangular solid. So yeah. And then I think, yeah, past this point in my notes I talk about deeper things like Green's identities and the Helmholtz theorem. And these are, the goal of this part of the notes, if you're interested, is to try to explain why the construction of potential energy functions, or the so-called vector potential that you study in magnetostatics, is in fact reasonable, and the integrals that we share in physics are not just physically natural, they're also, they have a mathematical basis in this mathematics. Anyway, that's it, and I mean, you probably need to see more examples. Sorry I haven't given you more, but if you want to see more examples, I have oodles of them already on the YouTube channel, and if you need help finding which one to look at, feel free to email me, I'll send you a link. So thanks guys.